I'm Pat Dugas. We're going to finish our coverage of polynomial functions with the rational zero theorem, which allows us to help zoom in on and find the rational zeros of a polynomial function. So let's jump right into the rational zero theorem. If I have a polynomial p of x and it has integer coefficients, then every rational zero, in other words, every zero that is a rational number, is in the form p over q, and that's a rational number in simplest form, where p is a factor of the constant term at the end, if it's in standard form, and q is a factor of the leading coefficient. And so every rational zero of, for example, this polynomial right here, is going to be a factor of negative 40 divided by a factor of 6. So for example, if 4 over 3 is a 0, if we know that 4 over 3 is a 0 of f of x, that must mean that 4, the p part, is a factor of negative 40, and the 3, the q part, is a factor of 6. Now it should be noted that the rational zero theorem only tells us the possible rational zeros of the function. It does not say the actual ones. You have to actually test it out, and we'll do that in a few minutes. Corollary to this, if you have a polynomial and the leading coefficient is 1, then basically what that's saying is that all the rational zeros have to be factors of the constant term, which kind of makes sense. It still fits in that p over q idea, because if q is the factors of 1, we're really just talking about positive or negative 1. And so the p basically takes over. So let's look at all the possible rational zeros of f of x equals 3x to the fourth minus x to the third plus 4. Now we know that there can be as many as 4 zeros to this because it's a fourth degree function. Okay, so if p over q is a rational zero, then the p has to be a factor of 4, positive 4, and the q has to be a factor of 3. What we do with this is we're going to list out all the possible factors of p and all the possible factors of q. And so all the possible rational zeros, it's a pretty long list because it's the list of everything in this row of p's factors divided by everything in this row of q's factors. So we got plus or minus 1, plus or minus 1 over 3, plus or minus 2, plus or minus 2 over 3, and then plus or minus 4, and plus or minus 4 over 3. Now again, that does not mean all of them are zeros, rational zeros. Certainly they're not, because at most this function can have is 4. We're going to look at an example where we actually test that out and use it to find these zeros. So let's look at all the possible rational zeros of x to the fourth plus 7x to the third minus 15. Well, we know the coefficient of x to the fourth is 1, and so that means all our zeros are factors of the constant term negative 15, which means that our possible rational zeros are plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15, all of which are the integer factors of negative 15. So let's kind of piece this all together, and we have a very big function here, x to the fourth plus x to the third minus 19x squared plus 11x plus 30. Now we should use things we already know, like Descartes' rule of signs, which we looked at in a previous screencast, to tell us about how many zeros we have. We know that there can be as many as 4 total complex roots from the fundamental theorem of algebra, previous screencast. Of those 4 complex roots, we know because of Descartes' rule of sign changes, and there are 2 positive sign changes here, we know there's 2 or 0 positive real roots, and if we put in a negative 1, and again that's previous screencast, we did the same thing for the negative, we would know there's either 2 or 0 negative real roots. So that kind of gives us an idea what the roots should look like. Now we're going to use the rational zero theorem. And since the coefficient of the leading term is 1, we're going to look at that positive 30. Again, that's p over q. The q is 1 in this case, so it's basically the p term that takes over. So there are, plus or minus 1, plus or minus 2, and so on, a lot of possible roots. 16 possible rational zeros. We know there's either 2 of them or none of them in the positive side, and 2 of them or none of them in the negative real side. So we start making a table. Well, just head down the list. If we looked at positive 1, we get a remainder of 24. If we put a positive 2 in, though, we get 0. So we then know that positive 2 is a 0 because f of 2 is equal to 0. Putting a 2 into this function yields 0. So once we divide that out, and again, that's a previous screencast as well, but if we divide that out of this polynomial using synthetic division, we would get what's called the depressed polynomial, which is after we've divided out x minus 2, x to the third plus 3x squared minus 13x minus 15. So what we do is we start plugging in the real zeros of it. We know that positive 2 is one of our zeros. And so we know there's one more positive 0 out there, so we continue down the line. And we're lucky enough that positive 3 is actually the next 0 by putting it into the depressed polynomial. So we've got our two positive zeros now. Our positive zeros are at x equals 2 and x equals 3. All we have to do now really is divide. If we divide out the x minus 3 into this depressed polynomial, we get another polynomial that's even shorter, x squared plus 6x plus 5. We can use another technique that we've looked at before, factoring. So I'm looking for things that multiply to give me 5 and add to give me 6. Well, how about positive 5 and positive 1? They multiply to give 5, they add to give 6. So we factor this, finding that x plus 5 times x plus 1 is our solution to this polynomial to find the other two zeros. And of course that leads to using the zero product property, x equals negative 5 and x equals negative 1. Those are our two negative zeros. X equals negative 5 and x equals negative 1. And that's all there is. We know there can't be any more than 4 real roots. In fact, all of them happen to be rational real roots as well that we found through breaking down through the rational zero theorem. So we looked at the rational zero theorem, which is another tool to help us identify zeros, specifically the rational real zeros in a polynomial.